On the back side. Thanks. Thanks, Slide. I appreciate this.
Yeah. That one is.
Okay, so homework 1 is posted. It'll be due in 2 weeks from today, if I calculated correctly. I often get dates wrong. I don't think I did this time, February 22nd. Let me take just a few minutes at the start of class to comment a bit on the problems. I think, first of all, don't be intimidated by the length. I think it's like 10 pages. But you'll see that 95% of that is text that I've written to explain the problem. And most of the text is redundant. It's simply explaining what I explained in class in words. So if you look at the first problem, it's about stochastic logic. I talk about AND gates, multiplying AND gates. I talk about mux implementing addition. I give an example. Then I talk about the Bernstein coefficient. So the first 3 pages is all information that was covered in lecture. And the problem statement itself is here. And so for those of you who have done the quiz, the problem statement is not scary at all. It's simply, here is a polynomial, and I want you to implement the polynomial the way that you did on the quiz, so transform it into a Bernstein form, et cetera, et cetera. But then I want you to sketch out the circuit, the corresponding circuit, in terms of the multiplexer and in terms of the coefficient. So sketch out this circuit, and then try it on specific input values. So choose input values with a certain probability and do the calculations and show that the output probability matches what the polynomial evaluates to. So you can ignore everything that came up until the end of page 3 if you've understood it or it's there for your reference. I think this problem should be very, very straightforward. Again, background material if you need it. There's a paper on the website that explains all about calculating the Bernstein coefficients. The slides from that lecture are up on the website that have the formulas, and the video from that lecture is up too. So I think you have everything you need. But any questions on this? I appreciate that you'll have questions when you've had a chance to look at it, but any questions off the top? Okay. Yes, your name is?
Handwriting this and turning it in, right?
You can do either. You can write it by hand, you can type it up, and the submission can either be by paper to me, or it can be by email to the TA. Email to the TA is just as convenient for us as turning it in on paper. But yes, there's no electronic submission, just email. Okay. All right, so the next problem, problem 2 is probably the trickiest problem. I would say it's certainly the trickiest problem. So this is the same familiar little circuit that you saw in the quiz. And those of you who took the quiz noticed the twist being that C is not independent. There are 2 copies of C. Hence, you can't just plug in the probability values and multiply them and then do the corresponding operation for the OR. You don't get the right answer. But here, what this problem asks you to consider is a completely different twist on the problem. So here, you're not considering you're not considering stochastic bit streams flowing in. So you're not considering zeros and ones streaming in. Instead, you're just looking at these circuits, and you're evaluating the probability that each gate computes correctly versus the probability that the gate computes incorrectly. So entirely different setup for the topic here, where we're not considering probabilities coming in. We're considering probabilities in terms of the gates producing the correct result. Now, what is the correct result? What's the incorrect result? Well, if an AND gate is supposed to evaluate to 1, that's the correct result. The incorrect result is obviously 0, or vice versa. So it's the gate failing in a specific artificial way. It's failing in the sense it produces the exact opposite value that it's supposed to produce. So I think for the non-computer engineering folks, there's no circuit analysis or circuit design here. It's a question of computing probabilities. And you'll see that it's not as easy as it might seem. Well, again, it wasn't as easy as it might seem for this little circuit, because this is what I calculated, that the probability, given a failure probability of epsilon for each gate, here's the formula that I computed for, can you guys read this or should I blow it up? Is this the Windows browser? So here is circuit A versus circuit B. And the formula that I give here is, assuming I did it correctly, this is the probability that the circuit A produces the incorrect result, given a probability epsilon that each gate produces an incorrect result. And you can see that for B, it's getting even more complicated. But critically, this probability is a function of the variables, C, or ABC. It's a function of the variables in the sense that if C is 0, then the probability is just epsilon. But if C is 1, it's not. And if you stare at the circuit for a moment, you'll see that makes sense. Okay. Now, so that circuit was tricky enough. But I ask you to do it on, and so here are the results in terms of plotting the values for different input combinations and the probability of failure in a comparison of A versus B. Now, what I ask you to do is to do exactly the analysis that I do on that small circuit for a slightly bigger circuit, this one here. So here, the non-computer engineering folks. I hope this is OK. So and and or, I told you what and or are. Exclusive or, I haven't. So let me take a moment to tell you what exclusive or is. So exclusive OR is a gate that is defined by this truth table. So if both inputs to the gate are 0, the output is 0. If either input is 1, but the other is 0, the output is 1. So far it behaves like an OR gate. Similarly, if the other one is 1 and the second one is 0, it's 1, like an OR gate. But the difference between an XOR gate and an OR gate is in the case where both inputs are 1, the output is 0. So it's called exclusive OR. So if you think of it, it's, well, what's a good metaphor? It's a different discussion. But in linguistics, and this varies from language to language, and I'd be interested to hear if anybody is a native speaker of another language where this differs. But in English, when people use OR, depending upon the context, more often than not, they actually mean exclusive OR. So when you ask a child, would you like chocolate ice cream or vanilla ice cream? The answer isn't yes, meaning they want both. It's one or the other. That's implicit. And in fact, or is usually in that context. But what's interesting is people who have a background in computer science specifically start to use or in everyday parlance to non-computer scientists to mean the other or function. So they sometimes will answer yes to an or question, and they look like retards. Because the question is, should I turn left or right? And the answer is yes, because it doesn't matter left or right, what they're trying to say. And the person just looks at them, what do you mean yes? But people they change the definition of or, because when you program computers, that's what the or function is. Anyways, so this is exclusive or. This circuit, I don't think a knowledge of any other bit of circuit is helpful here, except for the non-computer engineers. The concept of a truth table is useful. So what is the concept of a truth table? This is the truth table for a single gate. And so the truth table for a circuit would be the following. In this case, we have three inputs, we have two inputs, no, three inputs, x, y, and z. We have x, y, and z. The truth table is simply a way of describing the output of a circuit or the function that the circuit implements by listing all possible input combinations. It's 0 and 1 in binary, so we would list them all. We start at 0, 0, 0. So these are all possible input combinations. Then the truth table would specify for a given output, like we have S and C, it would specify what the values are. So the values would be 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. I just happen to know this one off by heart, if I got it right. But is this okay? Now, I'm just trying to anticipate what I think is intuitive and makes sense to the world, but doesn't make sense to somebody who hasn't studied the topic. So this is how, as a function of the variables, you describe the outputs. To arrive at this, you plug in the zeros or ones into the variables, and you just evaluate each gate. And then you have zeros and ones on the outputs of those gates, plug in those zeros and ones to the next gates, and just keep going to the outputs. And that's how you would arrive at this truth table. I think that's all you have to know. Then the exercise is calculating in terms of probabilities, where you have to look at all 8 combinations and formulate things in terms of epsilons. To be honest, this problem is a real pain. So you'll see the other 3 problems are easy. This one is not. It's a simple circuit. Do it up until, well, do the best you can with it. But don't stay up all night trying to work this out if it's getting too difficult. I don't know how to put this. Take a look at it, and then if you have questions, come talk. Okay. All right. The next problem is super straightforward. Again, a couple of pages, maybe a page and a half. In this case, it's only a page of explanation of the context, but I'm just describing exactly what I spent a few lectures describing, which is how, given 4 terminal switches, we can implement functions in terms of connectivity between top to bottom. And all you have to do for the problem, there are 4 examples. You have to take these 5 separate functions and implement them this way. Now, looking at them, some of them are straightforward. Well, I guess none of this is straightforward to non-computer engineering students. Why? Because you have to do a couple of things. First of all, you have to convert them into a sum of products form. And secondly, you have to compute the dual. But let me show you how to do this without doing it. So there's a program on the website that will do all of this for you. And you should use the program if you're so inclined. So first of all, this particular symbol, this is the exclusive OR symbol in the expression. So here's how you can compute the functions that you need. Go to the website, which I hope is here. If you go to the course website and you go on the left-hand side, there's tools. Click on that. Then click on symbol and click on the online part. So the tool is called symbol. And here's how you can use it. So if we had an expression like, I don't know, if we had A, this is an interesting keyboard. Is this not an American keyboard? But I'm having troubles getting plus. No. Where is plus normally? Okay, it's here, there. It's just not listed on the key here. I've got to look over at that keyboard. What nationality keyboard is this? Interesting. If you guys saw the keyboard, none of the symbols are in the right place. Okay, so just any of the expressions on the homework, you can just come to this page and type them in. Check off the little box that says SOP at the bottom, and then click Submit, and it'll take the function, including parentheses, and give it to you in a sum of products form, which, recall, is exactly what you need. The exclusive OR operation is represented here as the caret operation. So here, this would give us the sum of products corresponding to the caret operation. The apostrophe represents a negation in the expression. Now, just another caveat, put spaces between adjacent letters because if you just type in AB, it'll think that AB is a variable name. So you can name your variables fox, chicken, whatever you want. But people will make that mistake. If you put AB together, it'll just treat AB as a single name. So don't make that mistake. I should have that big disclaimer at the top. Okay, so you can just take the functions from the homework assignment, type them in here, you'll get them in sum of products form. But you also need the dual for this method. So can anyone suggest how we can compute the dual using this tool? Yeah, so what we should do is negate all the variables and negate the function. So if we wanted to compute the dual of this particular one, we would just type in, instead, so to get the function g, we would type in a, where is apostrophe? It's where the umlaut is on this keyboard. And then beware of parentheses. So now I want to complement everything, so I should put everything in parentheses. It's above the 9, right? There we go. Okay. Okay. So this. What? Why did it all go away? Like somebody who's never typed in my life. Thank you. Above the 0. Okay. All right. So now this should give us G. Okay. So that's how you get F. That's how you get G. And then for the homework problem, you have to look up the method for laying out the variables from F and from G, given it's in sum of products form, into the array. So that's all you have to do for that problem. So that problem's super straightforward, I think. Okay, the last problem, again, lots of write-up and description pertaining to percolation, description of percolation and what it does. But what you're asked to do here is to consider the percolation value for different models. The first model is very straightforward. You just have vertices in a graph, so vertices joined by edges. And you assume that each vertex has m neighbors, so it'll be a function of m and n. And the probability of a connectivity is p. And then as a function of n, m, and p, you're asked to find out what is the parameter for percolation. So this is an example of a problem where you can work it out by hand if you do calculations. And all I want here is an estimate, not a proof or anything. But it's also the type of problem, if you're so inclined, write a very simple program that does this. They'll just consist of, set it up with the probability calculations and a for loop. But I really think you can do it by hand. The next one is the same problem, but instead considering a point source with a radius. So the model of the cell phone users and whether percolation occurs across cell phone users set up that way. And for this one, you're asked to compute or estimate the percolation threshold, and this in terms of the radius r around each user. Okay. So those are the problems. So off the top of your head, any questions on these problems? Of course, I should open it up at the beginning of next lecture for questions. Anything off the top? Okay. In terms of grading and expectations, so let's see. If you do write a program, definitely turn in the program. Just attach it to your homework assignment. What I should state at the outset or discuss at the outset is the collaboration policy. So the collaboration policy is very flexible. meaning you are allowed and you're encouraged to collaborate. There will be some problems throughout the semester, just a few of them. Well, I'll mark them no collaboration. For those, the honor system, you're not allowed to collaborate. But on this homework assignment, you're allowed to collaborate on all four of the problems. But the distinction between collaborating and copying, those are not synonyms. And so it becomes difficult for the person grading it, in some cases, to distinguish between copying and collaborating. In general, I think those of you all of you have been in school for a while now, you know from experience that it can be very easy for someone who's grading anything to detect when someone has copied, who has cheated, even if the person thinks they've changed the values around. Just because if you're copying from somebody who has followed a certain path in solving a problem, even a straightforward problem, that tends to be unique in certain specific ways, like certain errors or so forth, and when someone copies, it's easy to spot. But in this case, since you are allowed to collaborate, it's hard for us to hold that against you. But this said, here's the model that I would like for collaboration. You're allowed to get together and discuss the problem. You're allowed to explain your insights to your friend and have them explain it to you. But here's what you should do. You can get together and you can discuss it, and you can discuss all the problems in as much detail as you want. But you shouldn't write anything down. Then, when it comes time to write your solution, you should go your separate ways. So you shouldn't be writing down your solutions together. If you think of it, doing it this way, you're in no danger of being accused of copying. Okay, any questions on that policy? I don't know how to state this, because this course is entirely homework-based, and collaboration is allowed. So there's a very distinct possibility that there's some people who are going to do no work at all and get an A. And if you do that, you won't go to heaven. That's all I can say. Okay, let's turn to the topic. And this is coming from a committed atheist, by the way. Okay.
Excuse me, Professor?
Yes?
Are we allowed to resubmit the homeworks on that basis?
No. No, unfortunately not. Just the burden of grading the homeworks is such that we can't have that back and forth. So no. Yeah. But definitely you're given 2 weeks to do this one, which I think is a fair amount of time. For the remaining ones, I see how I space it out. I think you'll have 2.5 or 3 weeks. So that's enough lead time that, I know this is easier said than done, because if you're like me, it's basically irrelevant how much time you're given. It's always compressed at the end. But there are lots of resources. There's me, there's other students. So if you're really stumped by a problem, this is the sort of course where, unlike an exam, even if you're not on top of the material, you can recover by seeking help. And I'm definitely very pleased to answer all questions. Okay, let's talk about today, as an introduction, computing with molecules. So this will be a very gentle introduction. And in fact, in today's lecture, I won't be talking about how we structure computation with molecular reactions. I'll be just describing the rules for evaluating the results of abstract chemical reactions. And today, and this will be the only time that I talk about techniques for simulating chemical reactions. But I'll talk about certain algorithmic aspects given a set of chemical reactions, how you simulate what's going on. It's my own take on it, and I think it has some interesting algorithmic aspects. But to be honest, I'm much more interested in the question of how can we design a set of molecular reactions to compute things. So bear with me for a lecture or lecture and a half where I'll talk about not how you synthesize reactions, but how you analyze them. But we do have to get on the same page there. So this is, and for the non-computer engineers in the audience, I appreciate your feedback on this, because you'll see that I'm probably simplifying things in ways that are insulting to you. My view of what a chemical reaction is, it's just a rule that specifies how types of molecules combine. So the rule might specify something like 2A plus B goes to C. So it's a rule that specifies if we have 2 molecules of A and then combines with 1 molecule of B, then we get 1 molecule of C. So think of hydrogen and oxygen combining to produce water. In general, such a reaction will be reversible. It'll always be reversible, I guess. But as it turns out, when I start talking about DNA-based reactions, some of the DNA-based reactions are effectively irreversible. The reason being is that the forward reaction has a much higher rate than the reverse reaction. Or intuitively, when you have single strands that combine to form double strands, it forms a very stable complex that basically doesn't break apart for all practical purposes. So a lot of the reactions I'll write as forward reactions only, even though a chemist would object that a reaction is always reversible. But from a computer science perspective, we can view a collection of chemical reactions operating on quantities of different molecular types like a finite state machine. So why? Let me open this to the floor. What was your name in the Nike shirt? Yeah.
Jared.
Jared. So Jared, what's a finite state machine?
Something that can only have one position.
Uh-huh. But what's the concept of a state?
True or false?
Uh,
Or a description?
Yeah. So a finite state machine in computer science or in computer engineering is a description of a circuit that has memory, but its memory is of very limited form. It just remembers the state that it's in. So the entire history is fully captured by the current state that it's in. For mathematicians, this also describes a Markov process, that all the information going forward is captured where you are presently. So with the finite state machine, there's a finite state, you're in a given state. That state tells you everything. But then you receive inputs, and based upon the inputs, you go to a new state, and you go through a sequence of states. The finite part is that there are only so many states, so you eventually have to hit a state that you've been in before. So here's a naive view of how chemical reactions within the confines of a cell or a test tube behave like a finite state machine. So suppose that we had 9 molecules of green, 6 of red, and 7 of blue. And we have a given rule. And that rule is that 1 of green combines with 1 of red to produce 2 of blue. Well, when this rule fires, we have 1 less of green, 1 less of red, and 2 more of blue. So we have an instantaneous state change. Previously, the state was, 9, 6, and 7. Then it instantaneously changes to 8, 5, and 9. And if there were only this rule operating, then it would operate, and we would go through a sequence of state transitions. So that's pretty simple. So what am I omitting here? The model is more complicated than this.
The reverse reaction.
Yeah, but we'll ignore those for now.
The reactions can happen in parallel.
They can happen in parallel. So we can have, in general, more than one rule, multiple rules. We have multiple rules, and those rules will fire in parallel, as Chris suggested, or at the very least, they'll fire at different rates, or one will fire more often than another. And so the rules are kind of the structural information of where we go from a given state to a next state. On the next slide, I'll describe multiple reactions in different rates. But also here, I'm making some huge simplifying assumptions that chemists or biologists can object to. One is, I'm assuming that everything I have is in a beaker, and I've shook the beaker. I'm assuming that everything is well stirred. I'm assuming complete spatial homogeneity, to use the jargon. And that assumption within the confines of a cell is definitely not true. Within the confines of a cell, you have tremendous amounts of structure. You've got all kinds of membranes, and you have the chemistry that's executing very much constrained and controlled by the physical structure around it. But it's a reasonable assumption to say that we're going to interpret these systems as finite state machines operating in a homogeneous environment. The discrete chemical kinetics part, this is something that to people who work in the area, they have this view that I'm assuming discrete chemical kinetics. So, Jesse, what's your view on my description, and why would you think that discrete is not accurate or accurate?
First of all, the number of molecules isn't going to be
9, 6, or 7, yeah. Avogadro's number. Yeah.
It's going to be significantly larger than that, and because of that, the fractionalization is going to be so fine that you're not going to have any discrete values.
Yeah.
You're not going to have 8, 5, 9.
Right. That's very good. So you described it perfectly. But some people, biologists, they don't have your perspective on it. They object even to the notion that at a truly physical level, there are discrete events going on. They view it as a continuous sequence of events going on. I'm not sure what they mean by continuous, but like Jesse said, in a lot of systems, you're dealing with a 10 to the, so nanomolars is going to be a typical quantity we're dealing with, which is 1 billionth, or nanomoles. So that's 1 billionth of a mole. A mole is 10 to the 23, so this would be 10 to the 14. So we'll have roughly 10 to the 14 molecules, which is a big number. It's not that big of a number, if you think of it. For a computer to count up to 10 to the 14, it wouldn't take that long. But just the very notion that things are happening in a discrete fashion, some people object to that view. I don't quite understand why. But everything else that Jesse said was absolutely correct, that it's not within our power to observe individual reactions in general. So in general, we will talk about simply the rates at which reactions happen. But coming back to Chris's comment about the model, the first important thing to note is in interesting systems, we won't have a single rule operating. We'll have multiple rules. And things are interesting when we have multiple rules, because then, as you'll see in a moment, we can have dynamics happening. But more importantly than that, we can also have different rates at which things happen. So we can have certain reactions that go slowly, others that go medium, others that go fast. And so different rates operating on different rules, operating on our finite state machine, that is essentially the toolbox that we have, or the set of toys that we have to play with to compute reactions. Okay, but stepping forward before I click next on the slide, slow, medium, and fast. So Jesse, how would you describe that? Slow, medium, and fast relative to what? Or what determines the rate of a reaction?
Well, there's something called the rate limiting step, rather.
If you have multiple reactions.
Sure.
But the rate limiting step is just, this is a rule of thumb, that the rate limiting step will limit the overall rule. Yeah.
Right. And in theory, all the reactions that most people look at are what we call global reactions, not the elementary reactions, which could be composed of tens of thousands of elementary reactions.
Yes.
And the biggest thing is it has chemical reaction rate has an exponential dependence on temperature.
Yeah.
So you can get orders of magnitude 20, 40 times
on temperature.
throughout basic chemical reactions.
Yeah.
So for slow, you could have reactions taking millennia.
Yeah.
Like isotope rearrangement, and fast reactions like combustion and other sorts that go faster than the speed of sound.
Okay, very, very good. You should be giving this lecture instead of me. But the one thing that you didn't mention is that the rate at which the reaction happens is dependent upon all the factors that Jesse described. But crucially, it's also dependent upon the quantities of the reactants. That the rate at which the reaction fires will depend in a very direct way on the concentrations or the quantities of the reactants. So I hope it comes on this slide. Here, this is just a repetition. But here, I've just repeated in a more concrete terms a set of reactions with A, B, and C. So we'll get to in a moment just my take on the formula for computing the rate. But so a set of reactions, what do I mean here by the set of reactions being coupled? And why is that interesting? And why would it not be interesting if they weren't coupled? So Jordan, what do I mean by coupled? And why wouldn't it be interesting if they were not coupled? I guess interesting is relative, but...
The next reaction depends on the products of the previous reaction.
Yeah, or that products are reactants, and reactants are products. So if we just had a system in which we had reactants going to products, and those reactions just went through, perhaps at different rates, it might be interesting to a chemical engineer, but it's not going to be interesting to us because we won't get the rich dynamics. But we can get very rich dynamics if we have products being reactants and reactants being products. It means that at first glance, if you look at such a system, it's analogous to a feedback system in electrical engineering where you have the outputs controlling the rate of the inputs. Then suddenly you can imagine you get interesting dynamics going. This is what we'll see, I think, next lecture. We'll see how you can get oscillations going. Oscillations are a lot of fun, where you can have a quantity going up and down and up and down. And as it turns out, you can have indefinite oscillations. And this was a result that shocked the world of chemistry. So do you guys know the history of this?
One of the first oscillation reactions is the iodine clock, which you'll have a solution that looks clear and it'll turn completely black, go back clear, and back and forth and back and forth. That one eventually terminates, but it was the beginning of a process of discovering.
And there's something called the BZ reaction, and there's an entire history of chemists, I guess inspired by physicists, concluded that perpetual motion was impossible. And when a certain physicist in Russia claimed that he had developed a system that would truly have perpetual oscillations, it was deemed to be impossible until years later it was accepted that this can happen. Anyways, that's definitely for a different course. We're going to focus on computational constructs. But as it turns out, setting up oscillation will be critical because we're going to use oscillation. So it was the iodine clock you described in a beaker. You can set it up so that it turns what color? Black and then white and black and then white. We're going to use that kind of oscillation as our clock. A clock in an electrical engineering sense, we're going to use that type of oscillation as a clock that synchronizes our circuits. Okay, but that's jumping ahead of ourselves. But just imagine to get oscillation, you need to have feedback in an electrical circuit. And in a chemical circuit, you need to have coupled reactions. Okay. So first of all, and here, maybe I should write it down. So let me write down on the board these reactions. We're going to do two things. First, we're going to look at a set of reactions like this, I think the conventional way, the chemists or chemical engineers would. We're going to go from this set of chemical reactions to a set of differential equations that describes it. And then after that, we're going to look at a second view, which is the so-called discrete or probabilistic view, where we're going to look at the system not as a set of differential equations, but rather as a sequence of discrete events. But first, the differential equations. So while I'm writing down a set of reactions before it comes next, somebody who doesn't know this off the top of their head. So Alex, why differential equations? How would you begin to set up a differential equation in terms of what goes on? So a little bit more information here. A plus 2B goes to 2C. That's a rule. One molecule of A combines with 2 of B to produce 2 of C. The K above it is called the rate constant, right? Which is stupid because it's not constant at all. It's dependent upon things like temperature. So it's stupid. I'm allowed to call terminology in another field stupid. But anyways, it's called the rate constant. So it's not constant in all, but it's a parameter that exists outside of the description of that rule. That's what K is. So the rate at which the reaction fires is going to be directly proportional to the rate constant K. It's also going to be directly proportional to the quantities of the reactants we have, or the concentrations. So that's going to be the rate. Now, how would you go from a description of a set of reactions like this to a set of differential equations that captures all of that? Just think about it for a second. I'll write down these reactions because we'll need them. Anyone? Alex or anyone else? Yes?
You can have something like the rate at which A and B is
Very good.
reducing is somehow related to the rate at which like, C is increasing.
Very good.
I mean, it's not going to be exactly addition or something, but
Uh-huh.
the rate at which this reduction should be like,
Uh-huh.
related to the increase of the.
Very good. So the crucial first part you had was the set of differential equations that we're going to have are going to have the form dA dt, dB dt, and dC dt. So we're going to have the rate at which A is changing is some formula, the rate at which B is changing is some formula, the rate at which C is changing is some formula. That's a really good start. But what specifically are those rates? How would you calculate them or begin to calculate them?
Won't they be related on the K?
They'll be related to the K. And so obviously, let's look at this. So the first reaction produces C, producing 2 molecules of C. So the rate at which C changes is going to involve K1 times something.
Yeah.
But notice that C is also consumed in this reaction. So it's going to involve also K2 and K3. So all 3 of the Ks are going to be involved multiplying quantities that determine the rates at which these reactions fire, and in turn the rates in which these different concentrations or quantities change. So anyone else? And for some of you, I know this is old hat. Yes, Jordan.
This question is are these 3 separate, I guess, global reactions?
Yes.
Okay, not elementary steps in one grand one.
They'd be elementary.
They'd be elementary?
By your analysis, yes.
So what would be the difference between grand or global?
Global reaction is something like combustion
Uh-huh.
Of like methane and oxygen.
Oh, I see, where the description has an implicit ordering in the steps.
What's going to happen is you're going to form millions or maybe just thousands of intermediate steps
Yeah.
or byproducts that maybe eventually go to some product. And you simplify it or zoom out to A plus 2B
Yeah, I see.
goes to 2C.
But so actually,
But
I'm describing this as elementary reactions, but we will implement them as the opposite of elementary. What's the opposite of elementary? Global. But I'll justify why it's okay to do it. It's because the paradigm of DNA strand displacement is so clean. So I'll show you how using, so with DNA strands, the double strands and the single strands displacing part of double strands, it's very clean. We have constructs of elementary reactions in terms of DNA that exactly emulate these global reactions. So was that an answer, Jordan? Yeah. So I'm describing them as though they're elementary reactions. In fact, they're going to be global reactions, but I'll justify why the global reactions behave like elementary reactions in a few slides. Okay. So here's the set of differential equations, and this is messed up again. Or maybe not. Maybe it was messed up and I typed it again. I had it properly formatted, but going between Mac and Windows, the equation editor results, it's 2015. You think that, so they have driverless cars. And I know, I'm criticizing other people, it's my fault. Anyways, here are ugly differential equations. I hope you guys can read them. So dA dt, and then the subscript, the underscore is the subscript, so that's 2 times K2. Okay, now that it's in front of you in ugly form. So what's your name in the back? It was with the blue hat.
Me?
Yeah.
Chopin.
Chopin. Okay, I'll remember that. So can you begin to, here's the set of reactions. And by the way, I seem to recall from last time I taught that there's a mistake in this, which I may or may not have corrected. So this will be good. So how does this set of reactions translate to that set of differential equations? Look at dA dt and look at, oh, and I should write down K1, K2, K3. What's going on?
So the ones that are negative sign are the ones which are consuming.
Sure. So if the molecular type is on the left-hand side, it's a reactant, which means it gets consumed. So the term in the expression for the rate of change of that type will be negative. K is always just a multiplicative factor. So K1, in this case, just multiplies the term. So negative K1, but then negative K1 times what? By the way, here, the brackets that I put around the molecular types, this is just to indicate the concentration of those types. It's kind of ugly notation. It would be reasonable to just omit it, but the idea is that A refers to the type, and brackets, parentheses, no brackets, refer to the concentration. So go for it, Chopin.
So in case we have more of A remaining, then the reaction will be going at a faster rate.
Right. So, but why is it B squared instead of just B?
So it's like we are consuming two molecules of B at the same time.
Yeah.
So as we keep reducing the concentration of B, the reaction should like keep reducing at an exponential rate.
Okay, very, very good.
So, and that will be determined by how many molecules we're actually consuming.
Okay, very good. So here, in another classroom I found a physical pointer that I should steal, because I like to physically point. But let me do this. Okay, so here we have A times B squared times K1. The reason for that is that we have the rate of this reaction being proportional to K1 and being proportional to the concentrations of the reactants, directly proportional to the concentration of A, and quadratically proportional to the concentration of B. And a negative sign because we're looking at A here, so A is consumed at that rate by this reaction. Now, there are two other terms in there, one involving K2 and one involving K3. So the one involving K2, the term will be positive because A is produced. We have two molecules of A being produced, and so we have 2 times what we're multiplying. We're multiplying K2, which is it's always directly proportional, times the concentration of B times the concentration of C, and so forth. That's how we just set up the reactions. Is this clear to everybody?
I'm not too sure about why we're multiplying 2 once and then we have 2 in the exponential. So when it's on the reactant side, we have it as an exponent, and when we have it on the product side,
that's a very good point. Because here, let's say I produced 100 of C. Well, the rate of this reaction in isolation doesn't depend upon what we're producing at all. So the rate of the reaction is not proportional to the concentrations of the products. But if we're producing 100 C, that means that this term contributes a factor of 100 Cs, molecules of C, each time it fires. Does that make sense? But any questions on this? Is it okay, Jesse? No? Okay, go for it. Help me out.
This is perhaps what, as a chemical engineer or chemist, you would first guess for your system. Mm-hmm. However, in most cases, it won't follow a simple square of the concentration, a cube of the concentration, or even a first power of the concentration. And the divergence of that will be called the reaction order with respect to that compound.
Yeah.
And it's almost never the stoichiometric coefficient.
Sure. Yeah.
But when making your approximations at first hand, we generally guess that.
Yeah.
But your explanation of the product side is good.
Okay. So fair enough. But an explanation of why this is a simplistic view or first guess is that chemistry is messy. So by definition, it's goopy, messy, and stinky. But an explanation, I suppose, is that just the very notion of a reaction happening, it's a rule. So when molecules collide, whether the reaction occurs and the products are produced is a very complicated function of the physical chemistry of going on. You've got molecules of very different shapes and very complicated physical chemistry. But anyways, this is going to be the level at which we're going to discuss what's going on. And it's a level that works for DNA strand displacement reactions. Again, I'll explain that to you in detail, but it's a very clean paradigm, and it's hence a paradigm that all of us non-biologists, non-chemists can understand and follow. Okay. But here is a different view. It's a view that, and it'll be interesting to have this discussion with Jesse, because the argument can be made that the view on the previous slide was more of an approximation than this view, and this view is closer to the actual physics of what's going on. So this view is that each rule and the dynamics can be expressed as a probability. And the probabilities that we'll calculate is that at each point in time, we're going to calculate which is the next reaction to fire. Now, that makes an assumption that we have an extremely fine-grained notion of time, meaning we have untold billions of molecules in our system, and we're going to say, well, which is the next reaction to occur, an individual reaction that will occur once and change the value slightly. And we're going to compute a probability value based upon that. Now, this method, I guess we shouldn't get too excited about the physics of the paradigm. But there are going to be two different ways in which we can simulate chemical reactions. This particular method is called the stochastic method. And again, it was a method that was very controversial when it was proposed in the 70s by a fellow named Dan Gillespie. It was controversial just because everybody had done it the other way, and he proposed doing it this way. His motivation for doing it this way is that in some systems, you actually do have small numbers of molecules. His first motivation. You really do. You can have big proteins, and within the confines of a cell, the number of copies of a given molecule that's some big protein might be surprisingly low. It might be in the thousands. When you're down at that level, then this might be the more accurate method. But what I find interesting, and I'll spend a lot of time discussing, is that if we accept this as our fundamental model, that chemistry is random, a bunch of molecules bouncing around, and which reaction happens next is a matter of chance, then that means that there's inherent randomness in the system. And the constructs that I'll show you will aim at computing things probabilistically by design. That's going to be the link with the previous topic. And in order to analyze such a system, if we express it as a set of differential equations, well, the differential equations are deterministic. We'll never get probabilistic behavior out of a set of differential equations. So hence the stochastic method. This will make more sense after we explain it and I start to show you some examples. But to step through this a bit, so how does the probabilistic method work? Well, for a given set of reactants like this, we're going to compute the probability, and the probability is going to be proportional to two things. The rate constant, I really should have written that, the rate constant, K1, K2, and K3, as well as the number of ways that the reactants can combine. So what do I mean by that? Or can anyone guess, what is the formula going to be? So Jared?
Nothing off the top of my head.
So what I'm going to express on the next slide is so annoying, isn't it, that I ask you to predict what's right there. I just have to hit spacebar. So just lean back and why tax your brain? But I want to write down a formula for the probability of R1 being the next to fire, the probability of R2 being the next to fire, the probability of R3 being the next to fire. I want to write down a formula for that. It's going to be a function of K1, K2, and a K3. They're constant. But it's also going to be a function of the quantities of A, B, and C. But what is that formula going to be? Jason? Anyone else? So this, by the way, is a paper. So on the website, I'm beginning to assemble a set of recommended readings. And this is the first paper that I put up there on the biology side. I have 4 or 5 papers on the topics we've discussed till now.
Would it be something like conditional probability?
Close. It's going to be like a conditional probability in the sense we're going to normalize. So we're going to compute something for A, something for B, something for C, and the probability is going to be whatever it's going to be something for R1, something for R2, something for R3. And then the probability is going to be what we computed for R1 over what we computed of the sum of all 3. What's your name? Rishab and Chopin. Okay. So here's the formula, and I'm glad that the fonts are coming up. So suppose it's written in abstract terms here. If we have the ith reaction, Ri, suppose that the rth reaction has N1 molecules of X1 as reactants, plus N2 molecules of X2, so forth, and a rate of K. Then we're going to compute for the ith reaction. So we're going to do this calculation for each reaction. We're going to compute alpha I. What is alpha I? It's going to be K times X1 choose N1 times X2 choose N2, and so forth. Everybody knows what X1 choose N1 is. I went through it in the class, but it's the combinatorial, it's the binomial coefficient, the number of ways of choosing N1 molecules out of X1. Okay, now so that's alpha I. What's going to be the probability of reaction I? Rishab? And why?
Would be K into alpha I.
So, I hope I'm not losing people here. So it's simply going to be alpha I over the sum of all the alphas. So we're just going to normalize. So the alpha I here, it's called the propensity. And I don't know for a fact if this is a term specific to this field or if propensities is used generally for probability calculations. Does anyone know? Has anyone heard this? Yeah? It's probably in a similar context here. So it's a useful word. Like, I mean, if you look it up in the dictionary, propensity versus probability, I'm not sure there's an English, well, there probably is an English distinction. But the mathematical distinction is you compute a bunch of propensities, and then you obtain the probability by normalizing. So it's like, I mean, if your alphas all summed up to 100, then you would compute an alpha value, let's say, of 30. That's not the probability, but 30 divided by 100 is. So it's just the probability before you normalize. So it's quite intuitive, I think. But what is the propensity? Well, the propensity is something that's directly proportional to the rate constant, like before. And then it's essentially the same calculation as before, but not quite. So the calculation before was that, for the differential equations, that the rate of the reaction is proportional to the rate constant times the concentration of the reactants. If the coefficient is 1, just the concentration of the reactants. But if the coefficient of the reactant was greater than 1, it was going to be the concentration raised to that power. How is the binomial coefficient related to that? Anyone? John?
How is the binomial coefficient related to that?
Yeah.
Well, first off, I'm trying to figure out what you're doing because is X1 referring to the number of molecules you have? Because when you say that X1 is the species and N1 is the stoichiometric.
Yeah. Sorry, I'm just sloppy. I'm sloppy with my jargon here, with my notation. What I mean here is the quantity of X1.
Okay. So with binomial coefficient, you're referring to if you have said number of molecules, basically how many ways can you get the number you need out of there?
Right.
And so by multiplying those together times k, you're coming up with some sort of chance of that happening.
So let's suppose all the coefficients were 1. So if n1 was 1, n2 was 1, then the propensity would just be k times the concentration of x1 times the concentration of x2. So it would be exactly what we had before. The difference is, let's look at And implicitly here, we're going to have well, that's not a requirement, but we're going to have relatively small numbers for these coefficients. So we're not going to have 1,000 molecules of X1 participates. So implicitly, I guess we do have elementary reactions here. But if we have, let's say, 1,000 molecules of X1, and the coefficient is 2X1 plus something, then what we're going to compute is 1,000 choose 2. What is 1,000 choose 2? Someone help me out with the formula, John?
I don't know the formula.
This is what it sounds like in the brain of a schizophrenic. So it's going to be 1,000 times 999 divided by 2, right? So it's going to be 1/2 times 1,000 times 1,000 minus 1. This is, did I get that wrong? Okay, I saw some concern. But so this is roughly equal to 1/2 times 1,000 squared. And the critical part is that we have 1,000, which is a concentration of X raised to the power. And the dirty secret is that the 1/2 factor is simply going to be consumed into the K of the expression. So the Ks that we have, the rate constants, we'll use a slightly different formula for computing the Ks here as we did in the previous case. But I'm not going to be able to give a good explanation of this. But if you read the paper by Gillespie, he'll explain why this is an accurate physical model of what's going on. If you just assume the billiard ball model. So this is a naive view of chemistry. And help me out, Jesse, here, agree or disagree. Suppose you've got molecules of gas in a container. Everything is idealized. And it's idealized in the sense that a reaction happens if the reactants collide. And that's it. And the K factor, completely takes into account how likely the reaction is to happen if they collide. Then, based upon that model, how will you compute the probability that a given reaction, which is a rule, will be the next one to fire? Well, it'll be proportional to K, and it'll be proportional to the concentration of your reactants, or the quantity of your reactants. And if you have multiple copies that are needed to participate, it'll be proportional to the square of the quantities. Now, you're saying to yourself, well, that doesn't sound right, because if a reaction requires 3 molecules to simultaneously collide, and by the way, in an elementary sense, those reactions exist, apparently, but they're extremely rare. What typically happens is you have 1 molecule that breaks apart, or you have 2 molecules that come together. A reaction that requires 3 molecules to simultaneously collide may or may not even occur in nature. But the point is, if you do have 2 molecules of a given type that have to participate, then you might say to yourself, well, it's that much less likely for the reaction to happen. That's true. But this is Chopin's argument from before, that what we're interested in here is the proportionality of what's going on. And the more that we have of a given type, like X1, we want a quadratic proportionality to the probability of that reaction happening. But the overall rate will be compensated by a much lower K value for a reaction that involves 3 versus 2. Okay. I don't know if I'm losing you guys here. Anyways, in terms of the rule of what we're going to do, it'll be easy. To compute the probability of a reaction happening, we're just going to compute it as K1 times and let's switch from the terminology of concentration to quantity here, because this only really makes sense if we have relatively small quantities. It'll be the quantity of X1, choose N1, which is the coefficient, the quantity of X2, choose N2, and so forth. So the calculation then is simple. We just compute each alpha and divide by the sum of the alphas, and that gives us the probability that that reaction is the next one to fire. Okay, then what do we do? So we've computed a bunch of probabilities. How does that help us characterize what's going on, John? Or what's your name? Suesh.
Biswesh.
Biswesh. Okay.
You could model the chemical
chemical reaction is a Markov
Yeah.
process.
And so describe a bit how you'd model this as a Markov process.
Just have like, in a sense, each molecule has a state, and if it reacts and it's going to a different state.
I'm just trying to, okay. So suppose that we're in 555 as our quantities. Then what do we do? Just step us through it, because you'll have to do this on your next quiz or your next homework. Bishwesh, right?
That's the initial.
Yeah.
And
And the set of reactions, let's say it's this set.
is each 5 like number of molecules?
Yep. For A, B, and C.
And then there's a probability that like each will like turn into something else.
Yeah, so in the previous slide, what I tried to show is the formula for computing the probability that R1 is the next reaction to fire. So R1, R2, R3. On the previous slide, we had a formula for computing what is the probability that R1 is the next one to fire. We could actually do that calculation. It's pretty simple, but it's simply going to be so it's going to be let's say 1, 2, and 3. So it's going to be 1 times 5 times 5 choose 2. That's going to be the alpha I for this one. We compute the alpha, that's the alpha for this one. We compute the alpha for this one. We compute the alpha for this one. Then we compute the probability as the alpha for this one divided by the sum. So we get a number. But what I'm going at is, okay, so we have probabilities. But what do we do with them? How do you simulate a Markov model?
You can have a next stage of states, and then you can have probabilities associated with each transition.
Yeah, that's very painful. But it'll be a recurring topic that you're an electrical engineer. So your view is that if we have a Markov process, let's calculate what's going on. And you'll see, even for a system like this, believe it or not, the calculation is impossible. But we can do something that's very easy. We can simulate it. So how can we simulate it?
So you just give the probability of whichever rule fires, and then that tells you what the next state is going to be.
But what I'm getting at, or the question, maybe I'm prodding you guys a bit too hard. We have a bunch of probabilities. So what do we do with this? So
Generate a random number.
there you go. That's how you simulate it. These are called Monte Carlo simulations. What you do is you generate a bunch of probabilities, and then you pick one of the 3 events at random based upon the probability distribution that you computed. And you choose that reaction. So going forward a couple of slides, Gillespie is the person who proposed this algorithm. Let's say we're at 555. We compute the probability that R1 is the next to fire, R2 is the next to fire, R3 is the next to fire. We have some probability distribution. Let's say it's a half, a quarter, and a quarter. We pick a random number. So we pick a random number between 0 and 1. Let's say we pick the number, let's say we pick a number that lands right here. Then we choose R3. What do we do once we choose R3? Step us through it. Jacob or...
The rule tells you how much to decrease.
Right. So the other crucial amount is if R3 is the next to fire, that means we're going to go to a state where we have 1 less of A, 1 less of C, and 2 more of B. So we make that change, and then we do the whole process over again. So here I think I illustrate this. You've got R1, R2, and R3. 3 possibilities. One of them happens. So you compute all this, choose it. One of them happens. I'll discuss the time next. So one of them happens. And now you're in a new state. And now, unfortunately, you've got to repeat the probability calculations. Why, Jacob?
There's going to be different quantities.
Exactly. So the quantities have changed. Hence, the calculation of the alpha has changed. So in general, you have to recompute your alphas, recompute your probabilities. Again, make a random choice based upon the probabilities you computed. Go to some other state. Keep going. OK. Now, I guess I should let you guys go in a second. But what do you think happens next on my slide? Can you guess? John?
It
Close. If you had to draw a line on this slide that would be interesting, where would it go?
It can come back to the.
It can come back. So it can come back. And again, I'm sure the chemists will point out that since every reaction is reversible, it's not only possible that I'll return to a state that I was at earlier through some sequence of states, but I can go forward and backwards between two states. I can do this. But where I'm going next is that, this stochastic simulation, there's an expert here at the U, Yanis Kasnisis. He's the head of chemical engineering, right? He's an expert on he's not? I thought he was.
He's the head of graduate department.
Okay. Okay. Is Dan Frisbee the head of your department? Because I collaborate with him on flexible electronics. So just a side note, the ones and zeros, that paradigm, we're doing that for printed electronics. Okay. But stochastic simulation is something that people burn real supercomputer time on. Meaning, Yanis, he's one of the biggest consumer of supercomputing time on the MSI cluster. Why? Because he simulates chemical systems and biological systems this way. And it's incredibly time-consuming. And you can imagine why, because even if we have relatively small numbers of molecules, thousands or tens of thousands, we're tracking individual reactions. And so it's really burning supercomputer time. So what I wanted to talk about, and I guess I'll have to talk about it next time, is an idea. Here's the idea. If you look at how the simulation works, it's simple and quick to do each step. But here's what a given trajectory looks like. I'll really conclude with this. But a given trajectory in such a simulation looks like this. We start here, and we spend a lot of time going in little loops like this, a lot of time. But gradually we're making progress. So it looks like this. And what people are interested in doing this lengthy simulation on a supercomputer is here what I'm talking about in terms of the region is the state space. State space being, imagine that the values here are coordinates in space. And something happens when, let's say, one of your quantities goes above a certain threshold. Maybe what's plausible that could happen? In terms of a virus behavior, this is where the virus decides on one of its two reproductive strategies. So when a certain quantity crosses a threshold. But what the simulation is interested in is if you reach this quadrant, or if you started from here and instead, I'm doing this for emphasis, because there's lots of supercomputing time doing this. Or if you reach this quadrant. And what you're interested in is, do you reach this quadrant or this area of the state space or this area of the state space? That's what you're interested in. To get there, well, seems like you've got no choice. You've got to spend your time simulating each reaction, computing probabilities. But just as a teaser for next time, any ideas on what we could do to expedite the computation? Jesse, any ideas?
You could find a critical path or the shortest path.
The shortest path? Yeah. But absolutely. So, but the idea that I have is even simpler. But first, this is actually a very honest simulation, because what you're doing is chemistry, there is this back and forth, back and forth in terms of reversible reactions or in terms of, very locally reversible reactions. So what you're doing is simulating what's going on, so it's an accurate simulation. But by the same token, you're just computing things. And if you're just computing things, you're allowed to compute things faster than nature does it, as long as you don't make any mistakes. And so consider this. Suppose that we follow the simulation and we hit a cycle like this. And we notice that we've gone around the cycle. Maybe we've not noticed that we've gone around the cycle 100 times. Do we have to go around another 900 times? Let's say on average it takes 1,000 times. Or can we stop and say, I'm in a cycle. Let's figure out when I'm going to exit the cycle and exit right away. So anyways, that's the simulation technique that I'm going to describe. I'll describe that next Wednesday, I guess. But that'll be the last in the way of simulation, because that's not the focus here.
Why does that cycle end?
It cycles back if you think of it, well, because, but so the reactions are coupled. So we have reactants being products. So we have, if, you know, we have quantities being produced but then consumed. So it's very plausible that we can go back.
But this one, because this one, if I look at R2, it doesn't get you back to the one.
Oh, the problem is that it's not the same, R2. It does for this. I think it's set up for this one, which is different. Sorry.
You missed the last semester.
I only teach this in the spring semester. I know. It's great fun. It's just and great service that you guys are doing.
Yeah, you know, in the beginning, listening in on some of it. Really, like, intersecting a lot of
That's
things.
the intent.
Yeah, it's cool. I'm just graduating. I mean, I'm taking my master's in computer
In
science.
CS.
I'm kind of right in this place of stuff. I'm doing training machines right now. And yeah, it's almost like I wish I would have done some of that at the beginning.
Sure.
So it kind of like mature into things where I could really appreciate stuff like this. But it's really cool stuff. Yeah. Probably won't see me next spring.
Okay.
I just wanted to say,
All right, so leave this out here.